Greetings, everyone. Let's go further into simplifying radical expressions. Now, some of the things that are going to be expected of you for this skill are going to be these two previous skills here. First, you're going to need to understand the idea of like terms. You originally talk about this with variables, x plus 4x equals 5x, because they both share the same variable combination, and 1 plus 4 is 5. Okay? Same thing works for radicals. If it's the exact same radical, square root of 6 and square root of 6, then I can do the same thing. These would be like terms, so 1 plus 4 would equal 5. So square root of 6 plus 4 square root of 6 would be 5 square root of 6. Okay? So unlike, here's some examples for you. Things like x plus 4y, I can't simplify at all. So same thing. Square root of 6 plus 4 square root of 7, it's not the same radical. I can't simplify. Okay, third root of 6 plus 4 square root of 6. It's close, right? But third root and square root are not the same thing. So I can't simplify that either. Those would not be like terms. That's one skill you'll need for this. The other is, from a previous section, you need to understand how we simplify radicals by themselves using multiplication if possible, right? Like the square root of 20 is the same thing as the square root of 4 times the square root of 5. And the reason why I picked 4 times 5 is because the square root of 4 is 2. So I get 2 square root of 5. Or third root of 40 is the third root of 8 times the third root of 5. And again, I picked 8 times 5 because I can do the third root of 8 being 2. So 2 third root of 5. Okay? So these are skills that you'll need to go into this particular section and skill. Let's get started. Some examples here. Okay. So first example, 5 square root of 15 plus 2 square root of 15. Right? I'm following the file we have here. So this is just like the like terms that we had in the beginning. You can see the square root is the same. The 15 under the square root is the same. So they are the same radical. In which case, I'm going to get 7 square root of 15. And it's also important to notice that I can't simplify the square root of 15 any further because 15 is just 3 times 5, which are both prime. Right? So I can't simplify this any further, and this is as simple as it can get. My next example is 6 square root of 10 minus 3 third root of 10. Okay, trick question. A lot like the unlike terms that we were talking about last time. Right? Don't be fooled just because the 10 is the same that these are going to be the same radical. They're not. The square root and the third root, right? Different radicals. So this is already simplified. It's already simplified. Done. Okay? So those are your two basic examples. Let's do an example now that's not just one step like that. So now I've got square root of 50 plus 5 square root of 18. So all I've really got here is two individual radicals that need to be simplified like in the previous skill, and then afterwards I'll see if they're like terms or not. So we're going to work individually here. 50, I'm going to break him down into whatever I can get a easy square root out of, right? Well, with 50, I can get 25 times 2, right? That's what 50 can break into. And again, the reason I picked the 25 is because I can do the square root of the 25, right? So square root of the 25 gives me 5, and then square root of 2 is left over. Plus, next I've got the square root of the 18. Don't forget this 5 out here is not part of the radical. So I'm just going to carry him along for part of the ride there. Now let's think. 18. I need to break that square root down into something that I can do a square root of. 18 can do 3 times 6, but 3 and 6, neither one of those are square numbers. How about 2 times 9, or 9 times 2? That would be great. So I'm going to be splitting this into square root of 9 times the square root of 2, right? Well, that's going to give me 3 square root of 2. And I put it in parentheses there because, remember, I still have the original 5 being multiplied, right? This was multiplication here, so it's still multiplication here. I need to simplify multiplication before I can add. So I have 5 square root of 2, and then here I've got 15 square root of 2, right? Are those like terms? Same square root, same number under the square root of 2, square root of 2, those are like terms. So I can do the 5 plus the 15 for a total of 20 square root of 2. And that's pretty much the idea behind most of these problems. I want to start out simplifying any individual radicals because we always want those simplified to begin with. And if you also happen to be able to combine some like terms, well, then that's even better, right? I can make it even more simple. Okay? Let's go on with the next example. I have third root of 24 minus 4 third root of 192 plus third root of 3. And square roots feel kind of natural because we do a lot of squaring of numbers. It's even in our times tables, right? Third root, let's go ahead and do the full process here. I know I'm dealing with third roots, so I'd really like to be able to see my third power number list, right? What do we mean by that? I mean, if I start cubing numbers, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216. Well, 216 is bigger than all of my numbers up here, so I don't really need to go any further, but always you can if you need to, or if it makes you more comfortable to, right? Okay, so I'm going to be looking at each individual one of these, right? The third root of 24. Which of these numbers would go into 24? The 8, right? So I'm going to split this into third root of 8 times third root of 3. That's 8 times 3 is 24. Okay, well, third root of 8, that also comes from my list, right? 2 cubed is 8, so the third root of 8 must be 2. So now I've got 2 third root of 3 for this one, right? And I'm going to carry the minus 4 down right here, right? Because this multiplication is going to continue on. Okay, so let's keep going. Which one of these numbers would go into the 192, right? Does 8 go into it? Does 27 go into it? To be honest with you, you really should start on this end of the list. Because if you start on this end, you won't get the trouble of finding small pieces that you may have to do many of. If you go from the large end, you might grab the whole thing, or you will grab the whole thing in one chunk, because you'll find the biggest one that goes into 192. Well, 216 doesn't, right? Because it's bigger than 192. 125 into 192, right? Not likely, since it ends in a 2, and this one ends in a 5. And anything times a 5 is either going to give you the 0 or the 5. So that one's out also. What about 64, right? Well, 3 times 6 is 18, and 3 times 4 is 12. That adds up to 192, so it's 64. I'm going to split this into third root of 64 times third root of 3. Right? So then what do we have? The third root of 64 comes from the list there. That would be 4. And then the third root of 3 is left over. Okay, and then I've got third root of 3. Well, 3 is even smaller than 8, so none of my list numbers are going to break this down. Also, just flat out, 3 is prime, so I'm not going to be able to do anything with this. Right? So plus third root of 3 is already there. Let's simplify here. Don't forget the multiplication needs to be done first. So I've got 2 third root of 3 minus 16 third root of 3 plus another third root of 3. Okay? Go through and double check. Are all of these radicals like terms, right? They're all third roots. They all have a 3 under the third root. So they're all like terms. Thereby, I'll be doing 2 minus 16 plus 1, right? For a total of negative 13 times the third root of 3. Okay? Okay. So, same process as before. Don't let the higher root numbers throw you off. I'm going to always simplify the individual radicals, and then I'm always going to look for the like terms to be able to combine later. Okay. So let's get our next example in. Right? I've got the fourth root of 32 plus the square root of 32. Okay, in this case, you can already guess the root numbers are different. So I know I'm not going to be able to combine anything at the end. But the instructions are still the same. Simplify. So if I can simplify one of these, I need to, right? I've got a fourth root and a square root, so I'm going to be looking at two different lists, right? Let's do the fourth power list first. 2 to the fourth is 16. 3 to the fourth is 81. Well, 81 is already bigger than 32, right? So I've only got one hope, and that is if 16 were to go into 32. Lo and behold, it does, right? So in this case, I'll be splitting this into the fourth root of 16 times the fourth root of 2, because 16 times 2 is 32. Okay, and then from there, the fourth root of 16 we already know is 2. Fourth root of 2, like so. Okay, and then square root, right? So then we're just going to focus in on our square numbers, not to get them confused with the fourth power numbers, right? 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. 36 is already bigger than 32, so let's go back down the list, right? If I keep going back down the list, I'll notice there's that 16 again, just by coincidence, right? 16 goes into 32, we know that. So I'll be doing the square root of 16 times the square root of 2, because it's square root here, not fourth. And then the square root of 16 is 4, and I'm left with the square root of 2 there. So then I get down, and everything is individually simplified. But the fourth root of 2 and the square root of 2 are not like terms, so I can't combine those. So then the problem is then finished. It is simplified to our best ability. Okay. While you're doing these, from here on out with these examples, make sure you have your little list of numbers on the side, okay? Because that's what I'm going to be using to finish those out. Make sure you have your power lists on the side. Square root of 20x minus 6 square root of 16x plus 4 times square root of 45x. Okay? All right, so the only new thing here that we've added in is the variables. But remember our little check for those. If the power number is lower than the root number, in this case x is to the 1 power, and my root number is technically 2 because it's a square root. If the power on your variable is lower than the root number, then you have nothing to simplify, right? Because it's all about grouping groups of x, taking groups of x and making things. And I don't have enough to do anything because the power number is lower than the root number. So I won't be doing anything really with the variables other than just carrying them along here in this problem. But 20, I can split that one. I'm going to turn this into square root of 4 times the square root of 5x. And you could do square root of 5 and square root of x separately. I didn't see the purpose here though, because 5 and x are both left over after the square rooting process here. So I'm going to end up with 2 square root of 5x. Okay? Minus 6 times here. And then I've got square root of 16x. Well, that's lovely, right? Square root of 16, I don't have to break up. I can actually do the square root of the 16. And then we've got the same problem as before with the x. The power is lower than the root number. So the square root of 16 is 4. And then I've still got the square root of x. Don't make the mistake of forgetting that the x is under the radical, and it still will be. Okay, so plus 4 times, and then square root of 45. Let's go through our square numbers, right? Right, 4, 9, 16, wait a minute, 9, right? 9 goes into 45. So I'll be splitting that into square root of 9 times the square root of 5x, like so. Okay, so next step, let's continue simplifying. I've got 24 square root of just x here. And then the square root of 9 is 3. And then I still have to multiply it by the 4. So I'm going to end up with 12 square root of 5x. And everything else is still here. 24 square root of x and 2 square root of 5x. Okay, now look really closely. Right? Look at the radicals. At this point, I've got everything individually simplified, but are they like terms? Well, let's see. Square root of 5x, square root of x? Nope. Square root of x, square root of 5x? Mm-mm. Square root of 5x, square root of 5x? Yes, absolutely. So at this point, I can only combine the 2 plus 12 for a total of 14 square root of 5x. And then the rest is still there. Minus 24, and then just square root of x. Okay? So then this problem would be done, because I can't combine anything else, I can't simplify anything else. Okay? So don't forget to break these down as much as you need to see the pieces and where they're going. It's really at this point, if you understand the skill, beyond that, it's just bookkeeping, keeping up with all of the little pieces in each individual term. And then just making sure that you don't lose any of the pieces that are supposed to be under radicals, and later on also keeping up with what has to be like terms and combined. Okay, next example. What happens when we incorporate fractions? Uh-oh, I said a naughty F word, fractions. Be careful. Square root of 75 over 9 minus square root of 3 over 2. Well, the 9 and the 2 are fine. They're not even in radicals, right? So I'm just going to forget about those for now. However, in the back of my mind, I'm thinking I'm going to subtract some fractions here. It's possible we'll need a common denominator, but we can save that for later. Let's get the radicals done first, the more complicated piece here. Well, I look at the square root of 3, 3's prime. I'm not going to be able to break that down. So he's already simplified. However, square root of 75, though, we can break that down. What square number goes into 75. 4, 9, 16, 25, right? Yes. So, next step, this equals to square root of 25 times square root of 25 times what is 75? That would be 3 for 9. Minus square root of 3 over 2 is still there. Okay, so then what does this equal to? That's 5 square root of 3 over 9 minus square root of 3 over 2. Really tempting to make a mistake here. You see those square root of 3's and you're like, yes, like terms, going at them. 5 minus 1 is 4. No, don't do that, right? I have fractions here. They need a common denominator before you can do subtraction. So let's do that. 9 and 2, common denominator is 18. So I write my fractions down here, and then I go back and fix what I need to fix, right? Let's fix it. 9 times what is 18? That would be times 2. So I'd be doing a times 2 here, and remember you need to balance it in the top for a grand total in the numerator of 10 square root of 3. Okay, what about on the other side over here? 2 times what is 18? Well, that would be times 9. So I have to do the same thing up here, times 9. All right. So I have 9 square root of 3. Now the denominators are the same, the radicals are the same, everything is like terms. Now I can add, or subtract in this case, right? 10 minus 9, which is 1. So I have just square root of 3 over 18. Another mistake that you can be sure to avoid, the 3 and the 18 are not both in a radical. So I can't simplify that fraction, right? It's simplified right here, right now, the way it is. Okay, square root of 3 over 18. Okay? All right, so let's get another fraction example in here. Let's see what happens when I do the overall third root of the entire fraction 5x over 27 plus 4 times the third root of 5x. So we've got third roots this time to worry about. First things first, I want to break down the radicals as much as possible. And I'm noticing that 27 is in my third power list. That's one of the ones I can do the third root of immediately, right? So I'll go ahead and break this up. I've got third root of 5x over the third root of 27 plus, and I'll go ahead and start writing this as a fraction since I know we're going to be adding and we're going to need some fractional pieces here. Third root of 27, look at your third power list, right? What number multiplies 3 times to get 27? That's 3. And I still have 4 third root of 5x 1. Okay, so again, I'm noticing the radicals are like terms. They're both third roots. They're both of 5x. Great. But don't make that mistake yet, or ever, hopefully. Right? Common denominator is needed. What's common denominator between 3 and 1? That would be 3. So I just need to do a times 3 here and here in order to get that common denominator. So then equals, I've got third root of 5x over 3 plus 12 third root of 5x over 3. Common denominators, like term radicals, ready to add 1 plus 12. Grand total, 13 third root of 5x all over 3. Okay? So I'm hoping that you're seeing that it's really the same process over and over and over again. I simplify the individual radicals as needed, and then I look for anything that can be combined with like terms and hopefully simplified into one or the minimum number of objects, right? Okay. So then the next little set of problems deals with more than just adding and subtracting. So we're gonna shift gears now here just slightly to talking about multiplication with these radicals. So there is going to be some addition and subtraction here, but we need to talk about multiplying radicals with things that are more than just monomial radicals. They'll have more than one piece with different radicals. So here's the example I'm talking about. Square root of 2 times 6 plus the square root of 10. Okay, so the 6 plus square root of 10 I can't simplify at all, right? I can't simplify that. And so I'm left with just having to multiply the square root of 2 times the 6 plus square root of 10 in its entirety. But then that means we can just use distributive property, right? So my next step would just be 6 square root of 2 plus square root of 10 times square root of 2, which would give me square root of, right? They're both in square root. I can multiply them. 6 square root of 2 plus the square root of 20. Okay? And once you get to this point, you need to double check. We're back to where we were before. Can I simplify this anymore? Right? Now 6 square root of 2, no, because 2 is prime. But square root of 20, that was in one of the little examples earlier, right? I can simplify the square root of 20. That is square root of 4 times square root of 5. So I'm left with 6 square root of 2 plus 2 square root of 5. And in that point, I'm actually done, because the radicals are not like terms, so I can't simplify that any further. Okay? So we're talking about still doing the skills we were enforcing before, but now I'm throwing in multiplying the higher order types of radicals here, right? With a higher complexity with multiple pieces. Okay, so next I've got square root of 3 minus the square root of 5 times the square root of 2 plus 7. You'll notice now I've got two binomials, right? So then I'm going to need to employ what some people would call FOIL. I don't always call it that. I just call it multiplying everything to everything, or making sure that everything gets distributed, right? So what's really happening here is I'm going to distribute the square root of 3 to both, and then I'm also going to distribute the negative 5 to both, right? So I'm multiplying it out much like you would, polynomials. So square root of 3 times square root of 2 plus 7 times square root of 3 minus square root of 5 times square root of 2 minus 7 times square root of 5. Okay, so I'm just writing out all the pieces so you can see where I'm going with this. But over here, 3 times 2, of course, we've got square root of 6. 7 square root of 3 can't be, combined any more than that. Minus square root of 10. And then still minus 7 square root of 5 there. Now let's look really carefully. Are any of those radicals the same? Square root of 6, square root of 3, square root of 10, square root of 5. Nothing. So no like terms, and I can't simplify them individually. 6, 2 times 3, can't simplify that anymore. 10, 2 and 5, can't simplify that anymore. 5 is prime, 3 is prime. We're done. This is as simple as it can get, right? Sometimes that happens. We have multiple radicals, nothing in common, so that's all I can get. Okay, now this next example is something that comes up often with radicals. Okay? I'm multiplying two things that are conjugates. Conjugates are whenever you have these objects that are the same number pieces but have opposite operations combining them. So for example, square root of 5y plus 2, square root of 5y minus 2. Those are what we call conjugates. Okay? And you would have seen this word before when we talked about the difference of two squares, right? A squared minus b squared when we did our factoring lessons, right? And don't forget that the a squared minus b squared factored out into a minus b times a plus b, right? A throwback from our factoring sections there. Well, we're going to be doing it in reverse. Now I have the a minus b and the a plus b, and I'm going to be multiplying them out, which is going to give me something like a difference of squares. And this is actually what makes conjugates useful, because you'll notice at the end what's going to happen is I won't have any square roots left over. Okay, so let's go ahead and multiply this out like we did the last one. I've got square root of 5y times square root of 5y minus 2 times the square root of 5y plus 2 times the square root of 5y, right? That's here and here. And then 2 times negative 2 gives me negative 4. Okay? Now here, square root of 5y times the square root of 5y gives me the square root of 25y squared. And then I can simplify that concurrently here by doing the square root of the 25 and the square root of y squared. And don't forget, now technically this should be 5 times the absolute value of y. But you'll find that most of the time when we're doing these things, they'll either state it or it's assumed that all of our variables represent positive values. So here, you won't need the absolute values, and we'll just say 5y. Okay? Next, notice that the cross terms is what I call these, add out to 0, because I have minus 2 square root of 5y and plus 2 square root of 5y. They're like terms. Minus 2 and plus 2 equal to 0. And then I still have the minus 4. So all together, it comes out to be 5y minus 4. So as I was saying a moment ago, I'm taking advantage of the fact that square goes along with square root like an opposite, right? So if I end up doing conjugates like this, it tends to get rid of square roots. Multiplying conjugates gets rid of square roots. Okay, and that's a trick we employ with other things later on. So I just have the 5y minus 4, and then it's simplified. There's no more radicals there. Okay. Next, something that also needs to be shown really quickly is not to forget that when you square a binomial, you can't just square each piece. So if I have something like square root of 3 minus 7 all squared, I can't just square the square root of 3 and square the 7. This is a binomial. By definition, squaring is to multiply something by itself. So I write it out. And then I'm back to doing the distributing everything to everything like we were before. So I'll be distributing the square root of 3, which will get me square root of 3 times square root of 3, and minus 7 square root of 3. Then I'll also distribute the negative 7, which will get me minus 7 square root of 3, and plus 49. Square root of 3 times square root of 3 is just square root of 9, but square root of 9 is 3. So I've got 3. These two are like terms. Look, square root of 3 and square root of 3. Minus 7 is negative 14, square root of 3. And then I've still got plus 49. You'll notice these two don't have radicals, which also makes the 3 and the 49, quote unquote, like terms. So I can go ahead and combine those as well to finish up. I have 52 minus 14 square root of 3 once I add the 49 and the 3. And then I'm done with that particular problem. Okay? Okay, so to finish up, one last example of this same kind, but let's deal with some variables for a minute, because that's going to help us later when we start solving equations that have radicals in them. Sometimes you have to square something that might not be quite so nice to square, and this is an example of that. Square root of x plus 1 and then plus 2, and the whole thing squared. Okay? So technically this is a binomial because I'm treating the square root of x plus 1 like one chunk, one object, and then plus the 2 is the other piece. And since I'm squaring it, right, I have to write that thing twice and multiply it out. Like so. And then again, the FOIL, as some people call it, or distributing everything to everything. I've got square root of x plus 1 times the square root of x plus 1. I've got square root of x plus 1 times 2. So 2 square root of x plus 1. I've got 2 times the square root of x plus 1. So 2 square root of x plus 1. And then I've got 2 times 2. Right? Hopefully that's still 4. I didn't go to the meeting, but 2 times 2 is still 4, I'm sure of it. Okay, so let's do the easier side. Again, look, these two are like terms. They have the same radical. So I have 4 square root of x plus 1, and then the plus 4 is still there. And then here, I have 2 of these same things written twice. So you could think of it like this, the square root of x plus 1 squared. Right? And that's going to work out very much the same as it has in a couple of the previous problems. Whenever I deal with a square root and a square directly, right, I end up with the object inside the radical. And the same thing is true here. I would end up with the x plus 1 plus 4 square root of x plus 1 plus 4. Okay? And the thing to notice is now that the radical is gone from the x plus 1, the x and the 1 now technically count as separate terms. The x is not like terms with anything. The square root of x plus 1 is not like terms with anything. But the 1 and the 4 are like terms. Okay? So I'm finally left with here x plus 5 plus 4 square root of x plus 1. Okay? All right, I hope this was helpful in your endeavor to increase your skills in simplifying radicals. Have a good day.